Hi, it's me, Tim Dodd, the Everyday Astronaut. Welcome to Starbase, Texas. This is where SpaceX is building, testing, and even launching their Mars-bound rocket, Starship. Today I'm going to take you inside the gates and show you things that have never been shared outside of SpaceX. Best of all, we have the ultimate tour guide, Elon Musk, who answers all of my questions and gives us unbelievable insights to the rocket's development. We talked and walked around for over 2 hours, so I'll be cutting this up into 3 parts. The first 2 are at the Starbase Factory, and the last one is at the launch pad. Each section has a gold mine of valuable information, so make sure you're subscribed, you've got your notifications on, and you've got your notepads ready to jot some notes. Now, heads up, we talk about some pretty advanced concepts and subject matter that can be pretty intimidating on first listen, but don't worry, I've got you covered with lots of informational videos here on my channel. So perhaps if you're new to Starship, or really all of this stuff, consider watching my complete guide to Starship. That'll be a really good overview for you for some of the things that we talk about here in this conversation. And I'll also be linking to some of my other videos that will help out with some of the stuff that we talk about as well. Now you might notice we mentioned Soviet rocket engines quite a bit in this conversation. Maybe it's because I was wearing my new Soyuz shirt that you can get at everydayastronaut.com/shop, or perhaps it's because I've been working on a complete history and family tree of Soviet rocket engines for almost 2 years now. And that video is currently in the works and it will be out when it's done. And one last thing, this video is broken up into sections and we have links in the description for those sections. We also will occasionally be putting up a little map courtesy of Ring Watchers on Twitter that will help you keep your bearings as we're walking around. I think that'll help quite a bit. And we also have an article version of kind of our conversation and some of the key points that we bring up over at everydayastronaut.com. There's a link in the description to that as well. Okay, enough talking. Let's go hang out with Elon.
There's a camera, with a camera, and then somebody else with a camera.
It's just camera envy at this point. He's just trying to, he saw me with this and he's like, listen.
I'll get my camera out.
Yeah, you take a video of me.
I can take a video of this, of you guys taking a video.
Then you get over, make sure this is going through there.
Okay.
Just shoot the screen the whole time.
Okay.
I don't want anything else.
All right, so this is, okay, so I'm being videoed here, and then the video of the video. And this is the video of the video of the video.
Go back there.
Most of the camera's, is in the high bay and the mid bay right now.
Okay.
So I feel like I got here maybe at about the most exciting peak of insanity.
It's definitely a very exciting time because we are in a kind of a final push to complete the launch system, stage 0 essentially, and it's worth saying that the launch system, the tower, and the chopstick arms to catch the rocket are as complex as either of the stages.
Really?
So, yeah, absolutely, if not more. Like we could produce boosters and ships way easier than we could make the launch site. So therefore, I'd say it is harder certainly than any single booster or ship. Yeah.
Well, I think that's one of those things people don't even realize is the manufacturing out here. That's kind of one of those things that you harp on so much, is how that's so important, and that's in the long scheme the hardest part of all this. It's just the manufacturing.
Generally, manufacturing is underrated and design is overrated. So people generally think that there's this eureka moment of you come up with this idea and that's it. Now it's good, but the design, there's literally 1,000%, maybe 10,000% more work that goes into the production system than the thing itself. So say how much effort have we put into, say, designing Raptor versus designing the manufacturing system? It's 10 to 100 times more effort to design the manufacturing system than the engine.
Even of Raptor?
Oh yeah, absolutely, especially with Raptor. All of our, the amount of effort that goes into the design rounds down to 0.
Right.
Relative to the amount of effort that goes into the manufacturing system.
Yeah.
And if this was not true, great. I'd like 1,000 Raptors, please. Oh, you can't make them? Oh, okay.
Right.
This is like just very fundamentally underappreciated. If people have not been in manufacturing, especially manufacturing of something that's relatively new, then they don't understand, and they think the design is the hard part, and they think production is like a copier or something like that.
Right.
This is completely false.
Well, it's definitely not as sexy as the end thing. Like, you know, the end product is very sexy, and you know that's what draws people's attention. But the whole back end of it is what makes it possible.
I can't emphasize enough. I'm trying to correct the misperception that design is the hard part. It is not the hard part. There have been lots of great rocket engines designed. You've spent a lot of time looking at the Russian rocket engine designs. There's some amazing Russian rocket engine designs. They've been doing staged combustion for a long time, and they have done, I don't know, hundreds of different designs, literally. So the hard part is not can you design a staged combustion rocket engine. This has been done.
Yeah.
Now, admittedly, ours is higher pressure than before, and it is a full flow staged combustion. But that's a relatively minor increment relative to what the Russians have already done.
Right.
What is super hard about Raptor is how do we make a Raptor where the cost per ton of thrust is under $1,000? Yeah, I mean, we definitely don't want to. The fundamental thing that needs to be fixed is the cost per ton to orbit.
Yeah.
So things that address the cost per ton to orbit are good. Like, humanity will be a multi-planet species if we get cost per ton to orbit to the point where we can afford to become a space-faring civilization and a multi-planet species.
Right.
So this is, at its heart, it is fundamentally an optimization of cost per ton to orbit and then ultimately cost per ton to the surface of Mars.
Right. Well, and if you're working on getting the cost of, even when you're starting to think of it as dollar per ton of thrust, I mean, I don't know if anyone's ever considered that as a key metric.
Yeah.
You know, that's a new thing that I've never thought about, you know, never considered.
Yeah.
Well, and then even Raptor is kind of unique because now you're starting to also think about the, instead of thrust to weight ratio, when you have a fixed diameter and a fixed circle area, you're also worried about the nozzle exit to thrust ratio as being a pretty strong consideration too.
Yeah, you basically end up filling up all the area under the rocket. So with this version, we have 29 engines. There's a lot of beeping.
Yeah.
I'm not sure having this many things beep is actually helpful.
Right. Sensory overload.
Yeah, it's like everything around you is crying wolf.
If everything's in danger,
you just gotta tune it out. Yeah, exactly. So it's pretty silly, but.
So this is the nose of Booster 4.
Yeah, this is basically that's the interstage and the fuel tank of Booster 4.
Wow.
So yeah.
What are the little? So obviously those are where the grid fins go, right?
Yeah.
And then what's the thing in between them?
That's actually the mount point. So there are two. It's debatable whether this is the right design or not. In fact, it's like all designs are wrong, just a matter of how wrong. But that's one of the load points for picking up the booster. So that thing that you see, it's this like tiny little. It looks small.
Yeah, it looks like a.
But it's actually not that small like close up. This thing's just high in the air. Like all your sense of perspective is wrong.
Yeah.
And when this lands, it has like basically the density of a beer can.
Right.
You know, an empty beer can.
Right. What is the dry mass?
With like some mass, in the engines, obviously.
What is the dry mass? Are you under 200 tons for booster?
We should be under 200 tons. The mass is a moving target, so you also have to say like what are your propellant residuals when you land. That's a big deal. Like both how much margin will you have and what's your unusable propellant. Like you can't just go to zero margin, you know,
right?
Because the thing's gonna crater.
Yeah.
So it should be under 200 tons though. So, but as a rough rule of thumb, like the engines, including mounting mass, are roughly 2 tons. So if you've got 29 engines at 58 tons, then the sort of the fuel tank itself and the oxygen tank is probably on the order of Well, it's a little heavy right now, so maybe it's like 80 tons or so. Then you got the inner stage with we've got the grid fins, batteries, and a bunch of other things.
Yep.
So that's I don't know, maybe around 20 tons, and then you got propellant residuals, which might be on the order of 20 tons too.
Okay.
So
And
all that should come to, I don't know, call it 160 to 200 tons, depending on the sort of final mass numbers. But like right now, everything's too heavy. Like avionics too heavy. The
avionics even?
yeah.
I thought it was just a little.
I mean, it should be, but the grid fins are electrically powered, so we have batteries that are energy optimized instead of power optimized. So, like this grid fence only needs to work for like 2 or 3 minutes.
Right.
So it's very different from like a electric car, which you want to have several hours of driving. So these really we need power optimized batteries, not energy optimized batteries. This is just a short-term thing.
Right.
So the battery mass can probably drop by maybe a factor of 10.
Right.
So that's just one example.
Should we back up a little bit so it's a little. Yeah.
Less clanging.
Yeah. And everyone trying to get their cranes in here and do work. You got a lot of people on set right now.
Yeah, I mean, just like that residuals number is a super big deal on the mass, though, because the booster is designed to have 3,600 tons of propellant, which is in almost 80% oxygen, liquid oxygen by mass.
Yeah.
Like 78%.
Did you burn at what? Is it
It's like 3.5 to 3.7.
Okay. Yeah.
Wow. So, and you want to bias it in favor of oxygen because oxygen is denser and cheaper.
Right.
So in terms of improving your payload and reducing cost per ton, oxygen is basically plants make it for free and plankton.
Yeah.
So it's basically like electricity cost of separation and distillation.
Right. Now, remind me though, is it like, as far as the ratio goes, fuel OF ratio, having the lighter molecule? Don't you kind of want that to be spewing out faster or something because it's less reaction? You can accelerate it quicker. Or
yeah, there's a trade-off between. I mean, what you tend to get limited by is you don't want to go too close to stoichiometric because the heat's too. You basically melt your engine.
Yeah.
So that tends to limit you on the OF on trying to go to higher OF.
Right.
That's the actual thing limiting you. You tend to hit the stoichiometric melting point before you roll over on ISP.
Okay.
Generally.
Okay. That makes sense.
Yeah.
And remind me, are the grid fins? Do they still fold in?
No.
No. Is that going to be permanently that way?
Yeah. So what I'm trying to have us all just implement rigorously is the sort of 5-step process. First, make your requirements less dumb. Your requirements are definitely dumb. Does not matter who gave them to you. It's particularly dangerous if a smart person gave you the requirements because you might not question them enough.
Yeah, you might take it as like gospel, like
yes.
I have to do this thing.
Everyone's wrong, no matter who you are, everyone's wrong some of the time. So make your requirements less dumb. Then try very hard to delete the part or process. This is actually very important. If you're not occasionally adding things back in, you are not deleting enough.
Right.
The bias tends to be very strongly towards let's add this part or process step in case we need it. But you can basically make in case arguments for so many things. And for a rocket that is trying to achieve try to be the first fully reusable rocket. There's never been a fully reusable rocket. People don't understand. Like this is like the holy grail of rocketry.
100%.
Okay, and so you really need you have to run at tight margins because if you don't run tight margins, you're going to get nothing to orbit.
Right.
So you got to delete the part or process step. Super important, and you can't like hedge your bets. That's why the grid fins, for example, do not fold down, because that's a whole extra mechanism that we don't need.
And then compensate for it by having strong enough engine authority to steer it in the lower atmosphere.
Actually, our simulations, so we don't really need any extra engine authority. As long as the grid fins, basically follow the flow, they're not really disturbing the flow. It's really neither here nor there.
So
as long as they don't have a high angle of attack,
right.
It doesn't matter.
A few degrees or something, or within a degree or two.
So, but in any case, it's a thing we could add later.
Right.
So now these grid fins are humongous. We'll go see them, but they're like a dinosaur bear trap. Okay, it's like a bit of bear trap or a dinosaur. That's what these things look like. And if you have a whole mechanism for folding them, that's like clearly a part that we don't need.
Yep.
So this was a good design decision. That actually I didn't come up with, and it was like great, but it followed the principle of like delete the part, delete the process. And I was like, great, good idea. Let's not fold them. Why were we folding them anyway? Somewhat random, and also if whatever requirement or constraint you have, it must come with a name, not a department, because you can't ask the department. You have to ask a person, and that person who's putting forward the requirement or constraint must agree that they must take responsibility for that requirement. Otherwise, you can have a requirement that basically an intern 2 years ago randomly came up with off the cuff, and they're not even at the company anymore.
Right.
But it came from the, let's say, aero loads department. They're like, actually, no one in the aero loads department actually currently agrees with that. This is by the way happened several times.
So again, it can be literally.
I don't want to put it on the aero loads department, but it's every department.
Right.
So
it can be thought of as gospel again, but it might be something that's just totally in passing.
Yeah.
Or someone played too much Kerbal and had fins at the top of the rocket, and then it just, did this.
These things are often just way more silly than you'd think.
Yeah.
Anyway, so step 1, make your requirements less dumb. Step 2, delete the part or process step. If you're not deleting a part or process step at least 10% of the time, basically if you're not adding things back in 10% of the time, you're clearly not deleting enough.
Right.
And then only the third step is simplify or optimize. The third step, not the first step. The reason it's the third step is because it's very common. It's possibly the most common error of a smart engineer is to optimize a thing that should not exist.
Right.
Okay.
Right.
And you say, well, why would people do that? Well, everyone's been trained in high school and college that you got to answer the question, convergent logic.
Yep.
So you can't tell the professor your question is dumb, that you'll get a bad grade. You have to answer the question.
Yep.
So everyone's basically, without knowing it, they got like mental straitjacket on. That is, they'll work on optimizing the thing that should simply not exist.
Right. Right.
I'll give you an example from way back in the day of Falcon 1. So in the original sort of like when Tom Mueller and I were like batting around, like, okay, what should this rocket look like? I think I was literally in like Tom's kitchen or something, and we had like the spreadsheet and like, okay, we need to make a minimally viable rocket, like half a ton or whatever, it's something like that, and then initially the spreadsheet had we had an NTO MMH upper stage, so sort of hypergoal upper stage, kind of like a variant of the TRW LIMD.
Yep.
So.
Which I think Tom worked on, right?
Yeah, Tom, the people who trained Tom worked on it. He's not that old.
Yeah, that's right.
It was like a baby,
Yeah.
A very advanced baby.
He designed it.
But his mentors did work on LIMD. So, lunar module send engine. So, basically a pintle injector.
That's right, because that's where the pintle injector comes in, right?
Because you can also deep throttle it and everything. So, now the problem with that is how much does NTO MMH cost? It's super expensive. Okay, it's like a rare chemical. So even if you're like, if Edison and Tesla had a baby and that baby was smarter than both of them combined and said your job is to optimize an NTO MMH upper stage, you're screwed. Okay. So, like nitrogen tetroxide and monomethyl hydrazine are super expensive, and they're also toxic.
They're super nasty, yeah.
Yeah,
Just the handling costs alone are probably pretty
appreciable.
appreciable.
I do think like safety is overcorrected on the NTO MMH. It went from like nobody had any protection and breathed the fumes all day, to it's cyanide. Okay, and neither of those are true. It's not cyanide. You won't die. And Bill Gerstenmaier told me like a story of like when he started at NASA, they actually, I think, passed around like a cup of like hydrazine so that everyone knew what hydrazine smelled like. So like, because it has like a rotten egg smell or something like that. So literally an open cup of hydrazine, and like obviously he's still alive. So so that's an example of like don't optimize the thing that shouldn't exist. We should not have NTOMH upper stage.
Right.
Now Dragon does have that, but that's because Dragon's got to do a lot of like nuanced firings of the Draco engines, with very short pulse durations, and if you have trying to have something that's not hypergolic is very difficult, and it can be done. Like, but if you say not hypergolic and not cryogenic, now your options tend to suck.
Yeah.
So, then you start going down the peroxide, barking up the peroxide tree or something like that, and that's or super esoteric monoprops.
Right.
And that's like, again, back to big money. So
yeah. That's step 3.
Yeah. So exactly. So getting through these is quite laborious. Sorry for the laborious explanation here, but and then finally you get to step 4, which is accelerate cycle time. You're moving too slowly, go faster. But don't go faster until you have worked on the other 3 things first.
Gotcha.
Like if you're digging, your grave, don't dig it faster. Stop digging your grave.
Right.
But you can always make things go faster. And then the final step is automate. Now I have personally made the mistake of going backwards on all 5 steps, multiple times. So I have to repeat this. Yes, multiple times on Model 3, where literally I automated, accelerated, simplified, and then deleted. Like one example I've talked about before is like there were these like fiberglass mats on top of the Model 3 battery pack that were in between the floor pan and the battery. And it was at one point choking the battery pack production line, and I was like basically living on the battery pack production line, like trying to fix the line. Because it was like choking the entire Model 3 production program. So the first mistake was we should not have. I like try to fix the automation, like make the robot better, make it like the robot move faster, a shorter path, increase the torque, delete the reverse 720 degrees on the bolt, because that's unnecessary. Just go forward fast, not at 20% rate, at 100% rate. And instead of spackling glue on the entire battery pack, just put little dabs of glue, because the fiberglass mats are sandwiched between the battery pack and the floor pan anyway. So all you need is like something to hold them in place until you bolt the battery pack into the car.
Gotcha.
So automating was a mistake. Then accelerating was a mistake. Then optimizing was a mistake. And finally, I said, "What the hell are these mats for?" And I asked the battery safety team, because are these mats for what are these mats for? They said, "Oh, these mats." I said, "Are they for fire protection or something?" They said, "No, they're for noise and vibration, so you don't get." And I said, "But you're the battery department." Then I asked an NBA noise vibration harshness team, "What's it for?" They said, "Fire safety." So literally, it was like being in a Dilbert cartoon. Okay, it's like actually, I feel like I'm in a Dilbert cartoon quite frequently. So I'm like, are we in some simulation where I'm trapped in some like Kafkaesque / Dilbert cartoon situation? But that's what it feels like a lot. So then finally, okay, great. Let's try a car with the fiberglass mats and without, and they put a microphone in both, and see if you can tell the difference. You cannot. You cannot tell. In fact, I was like, which one is which? So we just deleted them and just bypassed this $2 million robot cell. It was just a complete pile of nonsense. Another mistake that tends to happen in production is too much in-process testing. So when you're first setting up a production line, you don't know where where things are breaking. You don't know where things are breaking, so you'll test like work in process at various steps, and because you want to isolate where's the mistake occurring. So a very common mistake issue with production lines is to have is to not remove the in-process testing after you've diagnosed where the problems are. So basically, if you have like a very high acceptance, if things are getting to end-of-line testing and are passing, then you don't need to do in-process testing. So, but what tends to happen is there'll be an initial development engineering team that will be basically debugging the production line, but then they will forget to take out the in-process testing steps. So then what happens is the in-process tester will often choke the cycle time, choke the line production time. It'll be like the limiter. It'll also have some number of false positives and false negatives. But I mean, like false positives, then you're rejecting good parts.
Right.
Really in volume production, if you have, if things are working well, you're really just taking a risk. Will this subsystem be rejected at during the production process or at the end? And so you just really want to move things pretty much almost always to just test at the end of the line, and that's it. Maybe there's one or two in-process steps that are hard to test at the end of line, but basically remove almost everything. There's another thing with battery pack where this is so crazy. One of the things the battery pack has to do is resist water ingress, so it has to be leak proof. So if you drive through deep water, water doesn't come into the battery pack and short out the battery pack. You might have seen some of the videos of people driving Teslas in extremely flooded waters,
just
where it's
this week, China.
half underwater. Yeah, people geez, there was literally a guy, I believe in Kazakhstan, literally drove a Model S through a submerged water tunnel, like it was, and all the other cars were out. And he basically steered the car with the wheels and used the wheel rotation to like a boat and drove out the tunnel. This is important to have the battery pack resist water ingress. But then instead of us doing a pressure test on the battery pack, we're actually pressurizing the inside of the battery pack, which was the wrong direction. And the battery pack lid was glued, was basically had resin that was not cured, and so we were just blurting out the resin, which doesn't make any damn sense.
Right.
Because you should actually be drawing a vacuum on the pack, and not pressurizing it.
Right.
And especially not pressurizing it when there's uncured resin is what's holding down the battery pack.
Yep.
So the pack was failing quite often on the pressurization test, which should have been a vacuum test. Anyway.
Speaking of grid fin.
Yeah, great.
Look at that. Man, that thing is huge.
Yeah, that's why I said it's like a
dinosaur bear trap.
Dinosaur bear trap.
Oh wait, that'd be just a dinosaur trap, wouldn't it?
Yes, it's a dinosaur trap.
That's insane.
Yeah.
Honestly,
this thing could catch a T-Rex.
Oh my gosh, that's crazy. And of course, it's got the serrated teeth, which help in the transonic regimes, right?
Yeah.
Is there any other reason for the teeth other than that?
No, it's just it actually helps in transonic and subsonic, but the effectiveness is better if you've got a pointy, if it's more pointy, basically. There is a limit to its pointiness. Sorry. Hey, Marvin. Yeah, exactly. It's crushed under a bear.
Wow. So how heavy are these guys?
Man, these are. I started to think. Actually, I don't know the number offhand, but probably at least 3 tons. I'm guessing. So eyeballing it. And this is not. This is why, when I say it's like a moving target, this is not the. I wouldn't take this to the bank. It's not. There's quite a lot of mass we can get out of this.
Right. 'Cause yours is just good enough for now. Like that's.
Yeah, it's good enough for now. But like, we basically just need like enough control authority to get this through the atmosphere and positioned well enough so that when the engine's light, the engine can correct whatever error is left after that we couldn't take out with the grid pins.
Right. Man, that is crazy. Those are huge.
Yeah.
And so it looks like the motor will mount to that lever arm there. Is that just a?
Yeah. So this is there's a motor this will basically be this will react onto the dome, basically the fuel dome. So there's like kind of like a C channel around the fuel dome at the top.
Yep.
And there's a motor that's going to rotate this with a gearbox. That's basically the load will be reacted between the circular feature that you see there and the sort of, I should say C channel, sort of L channel on the dome. So it's just a simple sort of ring on the dome.
Okay. And then is that, so what I'm seeing there where there's the ropes actually through it on the end here, is that the lever arm for the thing or is that just a?
Yeah.
Wow.
So
I see, it slides over. It's like a.
Yeah.
Okay.
That's basically that's where the motor will interact. So it's yeah.
Wow.
Yeah, but it's just basically we're just using like Model 3 motors basically.
Yeah. Which is so cool.
Might as well use them.
So you mentioned you're really trying to simplify it. There's been talks that they're not. Did you say it on Twitter that you weren't going to have you're going to eliminate the cold gas thrusters or hot gas thrusters on B4 for the first orbital test?
Yeah, but we can move to like maybe a more a quieter location.
Yeah.
I mean, I'm pretty sure we can cut the weight of that in half. Like that's, we're not even really trying to optimize the gauge. That's just basically plate. That's just like cut plate,
right?
Welded together. So we first just got to make the damn thing work, and then we'll optimize it.
Yeah, of course. Which again is something the Soviet Union was so good at. Was like minimum viable product, basically. Get it good enough to fly and test. And obviously you guys did that with Starship big time with 8, 9, 10, 11, 15 was like, let's just get it out there, see what works, see what doesn't, and iterate,
Yeah, and if you look at like the various reasons like where we blew up Starships, like, and you looked at the risk list, none of the reasons it blew up were on the risk list.
Really?
Yeah, there was like no. Maybe you could argue like one of them maybe was on somebody's risk list, but it wasn't brought up beforehand.
Right.
Put it that way.
Right.
I mean, there's a crazy amount of new technology happening here, and it's all evolving simultaneously. So we need to iron out like the unknowns, so to speak.
Yeah, the unknown unknowns are the big ones. And we got the new, is that the new flaps for 20 down there?
Yeah.
So, remind me the numbering scheme, because you were talking about version 2 Raptor the other day. What we've seen so far, are those version 2 yet, or not? Like the green nozzles, or those aren't version 2 yet, right? Have you started making version 2?
We've made parts of version 2.
Okay.
So we're going to make the thrust chamber assembly. We've made the thrust chamber assembly, and we have, I think, pretty much finished the design of the pumps. We're going to make the pumps. So hopefully we'll have, I don't know, Raptor 2, in about a month we might be testing the first one.
Okay.
So.
And will that be, you said, so you're going to be kind of producing stuff, or the prototypes are kind of going to be always in Hawthorne, then eventually you're going to be moving mass production to McGregor?
We're doing volume production of Raptor and McGregor, but we'll keep California factory operating. basically for development engines and the Raptor vacuum version.
Yeah, wrap back.
So yeah.
So if you're reaching 230 ton on version 2, what bar are you going to be? What's that going to be at? Like 330? 300 is
technically, I think 298, but I think we should. Come on, we got to like get 2 more bar out of that thing.
Yeah.
So
wait. So even at only 300, big air quotes on 300, you're getting 230 already?
Yeah, but we're opening the throat and reducing the area ratio.
Okay.
So the extra thrust is there's a slight. I think we lose like 2 or 3 seconds of ISP, but we gain a lot more in thrust.
Yeah.
And the increase in thrust outweighs the slight drop in ISP.
Yeah, especially on the first stage.
Yeah.
Yeah. But what's the?
I mean, basically any thrust to weight below 1 is worthless.
It's worthless. Yeah.
Yeah.
So if you go from 0.4 to 0.5, it's a massive leap compared to even. Yeah. Yeah. Okay, so that makes total sense. So the wrap vac, what's that for thrust? Is it still around that same number, about 200 tons? But
no, the Raptor vacuum RVAC, we call it, it will actually be the 230 ton thrust number is the thrust at sea level of the sea level version of
version 2
of the. It's essentially like helpful to. And like some people like quibble about like why are you talking about thrust in tons? That's not technically a scientific thing. It's because you can do the math in your head really easily if you have a rocket in tons and thrust in tons.
Right, of course.
That's why. And newtons you got to like divide by 10 all the time.
Right.
This is like annoying.
Yeah.
And then you only get kilograms. Now you got to like divide by 10,000 to get tons.
Right,
this is ridiculous.
Yeah, it is.
Okay, so you're like, what? This is absurd.
Yeah.
Only a fool would use newtons, in my opinion, if they're designing a rocket. And like especially big rockets, because you just like have bazillion newtons. So
yeah.
But if you measure things in tons and you measure thrust in tons, now you know thrust to weight very easily.
Right.
So
is that like the only imperial thing you measure then?
No, these are
still metric tons.
Metric tons.
Okay.
Yeah.
That makes sense. Okay. I was getting nervous for a second.
Pressures in bar.
Yep.
And because everybody kind of knows like what's 1 atmosphere.
Yeah.
So Pascals is another trash unit. I hate Pascals. So why is it so tiny? It's absurd.
Right. We should have a whole segment of units that Elon hates, and it's just
it's like units that make understanding things more harder instead of easier.
Yeah.
But everyone understands like bar or an atmosphere essentially. And everyone understands, like people can get their mind around a ton. Like you have an intuitive sense for a ton.
Yeah.
Okay, like your car is like 2 tons.
Yeah.
Sure.
Yeah.
Like can't pick that up.
Some grasp. You have some context.
Yeah. If you got hit by a ton, you'd know what that meant. If you got hit by a Pascal, it's like I don't know, a mouse part. It's like 1 Pascal.
Right.
So.
Wow.
So because there's another important principle, which is that you really want everyone to be chief engineer. So that everyone is chief engineer means that people need to understand the system at a high level to know what they when they are making a bad optimization. It's like when they are say like this. We've done this many times where we've like put immense effort into reducing the engine mass, but hardly any effort into reducing propellant residuals, or like order of magnitude less effort into reducing propellant residuals, and then you land with a literal ton of unused fuel. And actually, we still kind of do that with Falcon 9. It has about a ton of unused fuel upon landing, which is pretty annoying.
Right. That's still not much in the grand scheme of everything. It's still not much, but that is, in context, though, it still is quite a bit, though.
Yeah, but like we'd spend so much effort getting a ton out of engines. Like, you know, that's sort of, whatever, like 130 kilograms per engine. Like that's 100, yeah. So 120-ish. So, yeah.
Wow, look, the sunsets out here are pretty hard to beat. That's insane. God, that's amazing. So, congrats on the HLS
solidifying a little more today?
That was cool. Geo is a staunch defender of good contracting.
Can we head over and check out the mock-up there? Because there's still a lot that we don't know about HLS, publicly at least. I assume that you know a decent amount more.
I don't know if I do, but...
Well, first off, I guess the most obvious one that I'm excited about is those thrusters.
Oh yes,
at the top.
Okay, so so the thrusters are a good example of running that algorithm I just mentioned, laboriously mentioned, which is a question of the requirements. Make the requirements less dumb, delete the part.
Yep.
So, when looking at what does the booster actually need to do with stage separation, if you put rotation into the stack before you turn off the main engines, so they're both rotating. They're going to rotate.
Which way? Sorry, like pitching and yaw.
Yeah. So like you got the integrated stack.
Yep.
We do this with
Starlink.
With Starlink.
Yes.
So we rotate the stage.
Okay.
And
it kind of flings it out.
Yes, but they basically have different amounts of inertia. It's initially rotational, moving to linear inertia. So they basically move at different rates. So if you rotate the thing, depending on where you are, you will move at a different speed.
Yep.
And so it automatically separates if you rotate, and then separates. So there's no actual separation mechanism for the Starlink satellites, and they technically can bump into each other, and occasionally do. But if they bump into each other at like 1 mile an hour, it doesn't matter.
Right.
So they just bounce off each other.
And they already made it through the pretty harsh environments of launch.
Yeah, it's fine. So, but like I'm pretty sure this might be the only we were like literally tossing 60 satellites off with like a bundle of hay, like dumping the rods that hold them down, like a hay bale, and just flinging them, and it's fine. They just separate, boot up, and go to their position. So.
And that's
anyway, so if you go to stage step, and instead of asking the attitude control thrusters, the reaction control thrusters to do the booster rotation, which is a lot of force, you have the main engines initiate a rotation.
Yep.
Now this is quite complex space ballet, because everything's got to happen in just the right way. But you basically initiate the rotation of the stack, stop the main engines, then the two will actually separate by themselves. And you need like a little bit of. We have like coal gas ACS or reaction control system. It's like depending on who you ask, it's a reaction control system or an attitude control system.
Right.
It's basically like small maneuvering thrusters.
Yep.
So you fire those on the ship. That gives you a little bit of maneuvering, and then on the booster we actually have quite a lot of ullage gas. Like basically you've got a lot of hot gaseous oxygen and hot methane, which actually have, if you've got a big enough area, it's got decent thrust and vacuum.
The
vents.
Just
the thing
literally
you use to vent the stage.
Yeah, so not in a separate hot gas bottle, but literally like the ullage of the main tanks.
Yes.
Okay.
So just use the ullage as your thrusters, and just control the orientation of the venting, so it is not just venting out sideways, but it is venting in a direction that is useful.
Work.
So, which can be sideways sometimes. Anyway, we've got like basically a lot of gas in this thing, and which we would have to actually just vent to vacuum anyway, because it's got too much gas.
Yep.
And that's just extra mass that you don't need.
Right.
So, so if you've got basically enough control authority because of the kicking the whole stack over before main engine cutoff, plus using the ullage gas to vent, then you don't need you don't need a separate hot gas thruster system. You don't even need a cold gas thruster system. You already have hot gas.
For the booster, right?
Delete
only
the question the requirements, delete the part.
Yes, yes. But this is only for the booster, right?
Yes. Although arguably, now you mention it, we might be wise to do this for the ship too.
How can you have? You'd think that because
at least mostly.
Because
well,
the tanks are what, 6 or 8 bar or something? The main tanks.
Yeah, they'll be like six-ish bar.
Okay, and so wouldn't those be pretty low pressure, low ISP gas thrusters if you're only doing the gas from there? Or is there some trick you can do to?
No, in vacuum, you don't it's different in atmosphere. So, like 6 bar in vacuum is actually decent. Like it's like common to have thrusters, in-space thrusters that are, let's say 8 bar. Like the Draco thrusters for that maneuver Dragon are operating around chamber pressure of around 8 or 9 bar.
What?
Yeah.
Really?
You don't need like Dragon's still in PSI, so it's like 120 to 130 PSI. Technically, it's a pressure pulse, but
right.
It's so 120 PSI is like roughly 8 bar ish, maybe 8.5 bar. So it's not that far from the tank pressure.
Right. So you don't even need to store the gas in an even higher, like in a bottle that's at like 200 bar or something. You don't even need to do that to operate RCS.
No. If you've got hot gas, first of all, we really want the ullage gas to be as hot as possible, up to the point where it is impacting the strength of the hull. Like we don't want to soften the metal so much that it pops, basically.
Right.
The hotter the gas is, the higher the ISP. So having hot gas is good, and it's already there, and you already have the pressure vessel,
right.
And you're going to chuck it away anyway.
Yeah.
So obviously, you should use it as additive to control.
So
like obviously. Now, initially you can't do this with the ship because everything's cryo. But once the ship is mostly empty and is delivered to orbit, it also is in the same situation with a lot of hot gas.
Yeah.
So actually, we should really be the vast majority of our maneuvering should be with the hot gas that's in the ship. We're gonna fix that.
Jeez. Okay. So the thrusters on HLS that are going to be around the ring, the renders showed like 24 or something of like, the landing.
Oh, those are different. That's for landing on the moon.
Okay, yeah. Are those pressure fed? Like, what are those? Do you have a name for them yet or anything?
Let's just say like this is the tentative design right now, but with the agreement of NASA, I think we may see that design evolve. Okay. And it may be better actually.
Right.
So. A big question here is like, can you land on the moon with the main engines, or do you need a separate thruster system that's way up there? Like basically, if you land with the main engine, are you going to dig a big ditch in the moon and then fall over because you landed in a ditch that you dug?
And you shot bullets.
It's like literally dig your own
basically.
grave.
Yeah.
That would be obviously bad,
Right.
So we don't want to dig our own grave and then fall in it.
Right.
But more analysis is like I think we could probably land with the main engine and not dig a grave and die in it, but we would have to prove that. Get something that's like, I don't know, the consistency of like lunar regolith and like something that's like a good analog of that, and then like land a ship in that and see how big is the hole that we dig.
Yeah.
If you've got low pressure engines that are high up, naturally you're gonna have you're not gonna dig a hole basically.
Right.
So that's kind of like the sure thing. But I think if we can prove that the main engines do not dig a giant hole, then we could land with the main engines, and then not have
and not have any of those.
Yeah.
The ring.
Yeah.
What about the? Are you gonna have any sea level Raptors on the lunar variant, or will you only have vacuum optimized? Because I assume, like on a normal Starship, even at stage separation, you'll probably light all 6 at first just to minimize gravity loss or something, right? So you'll still fire all 6, and then probably shut down the sea levels and let the vacuum optimize. You know, like they probably do what, like half the second stage burn time or something with sea level, or have you?
Well, so the vacuum engines don't gimbal.
Yep.
So you'd have to have something to provide the control authority. I mean, technically, you could say like, well, if you're in a low disturbance situation, like the moon has no atmosphere.
Right.
Man, this is beeping city.
Want to move on?
Yeah. So if you're not facing like a lot of atmospheric disturbances, then you need much less control authority, and you could probably land with 3 just by differential throttling of 3 engines.
Yep.
But if you lost any of the engines, you'd be toast.
Yep. Yep.
So probably makes sense to, I don't know, probably keep the same config, you know.
Or like you could even just have one in the middle that would offer, you know, a decent amount of gimbal authority and all that.
It depends on how much optimization we're aiming for here.
Right. Because you're only probably going to make one of these things, right? Or are you planning on like, is NASA wanting multiple, or, oh my word. So by the way, I think there's a good chance that ITAR and comms might not want all of this. Wait until you see part 2. It is unbelievable. And I promise I'm going to get it to you as soon as I can. Thank you, Elon, for spending so much time with me and allowing me to ask all of the questions I had. It was amazing. And thanks to the teams at SpaceX for allowing me to share this all with you. And thanks to Cosmic Perspective for helping shoot this and just kind of helping out all the time. Find them on YouTube and on Patreon as well. And I owe a huge thank you to my Patreon supporters for helping make this and everything else we do here at Everyday Astronaut possible. If you want access to our Discord channel, where we'll probably end up talking about this conversation a lot, or live streams, or lots of other fun stuff, head on over to patreon.com/everydayastronaut. And while you're online, be sure and check out our awesome web store, where you can find shirts like this, the R7/Semi-Orca/ the predecessor to Soyuz new shirt that we have that is awesome, as well as our new Mars hats. But you can also find some classics like the Full Flow Stage Combustion Cycle shirt and hoodie, and the Future Martian shirt, and schematics collection, and lots of other fun stuff. So head on over to everydayastronaut.com/shop. Thanks everybody, that's gonna do it for me. I'm Tim Dodd, the Everyday Astronaut, bringing space down to Earth for everyday people.